Hi everyone, in this video, this will be our second video on diffusivity inversion, and we'll do second order sensitivity analysis. In the previous video, I didn't introduce this term, but that's called first order sensitivity analysis, which basically just tells you how sensitive your misfit is to your model parameter to first order. Now we're going to do the Hessian, which is second order. The Lagrangian we introduced last time to compute the gradient was as follows. We had this misfit term. That's what we fundamentally want to take the derivative with respect to. We add a Tikhonov regularization term to smooth the problem a bit. And then finally, we had to introduce this Lagrange multiplier P to constrain the physics of our model. Then what we did is we took partial with respect to P, set it to 0, partial with respect to u, set it to 0, and then compute partial with respect to m. And these two constraints tell us that this partial derivative is actually equal to the full derivative. Similar to before, we want now, given an arbitrary direction that we'll call m tilde now, we want to compute the full derivative of this expression with respect to m for arbitrary direction m tilde. But, as before, we need to enforce constraints, and we want to use the adjoint state method because it can efficiently basically turn this equation, this full derivative, into a partial derivative. So we need to continue to enforce our forward problem, but we also have to now enforce that P satisfies our adjoint problem as before. In order to do that, we're going to introduce two new Lagrange multipliers, P tilde and U tilde, that are just replacing these hats. We're going to pick a direction similar to how we took an m hat. If we want a specific direction m tilde, we just replace this m hat with an m tilde. And this is just for notational convenience here. It'll become clearer later. So for now, we have these two Lagrange multipliers. This is what we want to take the gradient with respect to. This is the gradient. This is the gradient of phi in the m tilde direction. This constrains the forward problem. We have this Lagrange multiplier P tilde and this Lagrange multiplier U tilde. And this is what our equation looks like. So that was our gradient. This was our forward problem in the P tilde direction. And this was our adjoint problem in the U tilde direction. And we proceed just as before. We take the partial with respect to P, and we solve this equation for all P hat. So basically the point of this notation is that tilde is just saying, okay, well, that's the direction I'm taking something with respect, I'm taking in the direction of it. P hat will just reserve to mean we're really varying this over the whole space when we solve a problem. So you can think of P hat as being a true dummy variable, whereas tilde is something you're actually going to eventually have to solve for. So we take partial with respect to P, partial with respect to U, and then finally, just as before, once we solve those two, we only have to take a partial with respect to M, and it implicitly gives us the full derivative. And that's basically all there is to it with Hessian action. It's very similar. So let's go ahead and work this out. So partial with respect to P. And I'm going to keep the same color coding. That way it's clearer for you if you haven't seen this before, where each term is coming from. So for that blue term, that's the first term dies, and then we end with that. All terms die in that equation, in the yellow equation, and then finally we end with the first term goes away, u tilde plus LP hat dx equals 0 for all p hat in H01. And then you can simplify that further if you want. But basically, that now outputs us, this gives us, at that point, we have u tilde. It's now a fixed thing that we know. So now let's compute the partial with respect to u. So again, the same color coding above. Del u hat dot del p. For the second term, that is m del u hat dot del p tilde. And then for the orange term, everything should vanish. Oh, not quite, yeah. So then you'll end up with u hat, u tilde, dx here. That term vanishes. Everything except for this term vanishes in the last one. So then this gives you another problem that you can solve for p tilde. So then at this point we have, so m tilde was a direction that we were given at the start, then u tilde and p tilde. And then from the gradient part, we've already solved for u and p, and we knew m a priori, so we know these three and these three, we're ready to calculate the gradient. So then we just take the partial with respect to this. Just going to go ahead and copy this really quick. Don't make any mistakes here. So now we just take the partial with respect to m. So this is the integral. R del m hat dot del m tilde plus 0 plus m hat del u dot del p tilde minus 0 plus 0 plus m hat del u tilde dot del p dx, and then just to simplify, this is equal to the integral of r plus m hat del u dot del p tilde plus m hat del u tilde del p dx. And then finally, so that it's the same mechanics, you just have to be careful of making sure that you write these constraints out correctly and that your role of p tilde and u tilde is taken care of properly. So ultimately, when you take derivatives with respect to m, you're still only perturbing u, m, and p in this notational convention. Just try not to get confused with those. That's why I like this notation, is that once you pass this dummy to tilde and keep everything as hat, it becomes clearer, in my opinion, that you're always taking derivatives with it u, m, and p, even though you've introduced these new variables. So why does this work? So if this is our Lagrangian, it's very similar to why the adjoint state method a few videos ago. I explained why that works. It's the same sort of cancellation. So if I take this derivative, this full derivative, this is partial Lagrangian h with respect to m plus partial Lagrangian respect to p tilde, partial m, and finally plus partial h partial u tilde, sorry, partial m. So let's look at partial Lagrangian with respect to p tilde. And the only term that has the p tilde is the fact that we've put that in that direction. So if we take that derivative, this is just the partial of the gradient's Lagrangian with respect to p. That's 0. Partial Lagrangian h with respect to u tilde. Similarly, this is the only term that has the u tilde in it. And this is the partial of the gradient's Lagrangian with respect to, u, because that's, we were constraining that. So those two terms vanish. Okay? And then finally, if we're saying that we constrain partial Lagrangian with respect to u is 0, then this vanishes. And if we constrain that this is 0, then it also vanishes. So we solve u tilde such that this is true, and if we solve p tilde such that that's true, then we get that we can evaluate it as if it's a partial derivative, just like before. So this is just to show you that these are the right equations. These two constraints are precisely what we need for everything to work out properly with the proper cancellation. So in the next video, I'll show you how to discretize this and actually show you how does it actually relate to the discrete optimization that we were talking about